Hello. Today, in this video, I'd like to talk to you about acids and bases. We're going to first do an introduction by talking about what acids and bases are, different theories of acids and bases, and see what we can recall about their different properties. Then we're going to introduce what a strong and a weak acid and base are, talking about what is different and what makes something strong versus weak. We're then going to use that to propel us into talking about acid and base equilibria, seeing some examples, and then finally discussing conjugate acids and bases. Well, first off, let's talk about what an acid and a base is. Now, one of my favorite acids, got hydrochloric acid right here, HCl, a common one we use in the laboratory. If I have HCl, we all know what HCl makes in solution, besides knowing its properties. Acids go ahead and they dissociate to make H plus ions in solution. So we might recognize an equation like that. Now, if we wrote this more generally, we could say that HA, where A is just any anion, is going to make H plus A minus. My anion is now actually an anion. Now, I want you to contrast that with a different acid. I also have here vinegar, acetic acid, something we've also seen before. Now, acetic acid is HC2H3O2, and that has a bit of a different dissociation. And you're going to notice we draw it differently. The difference between these two reactions is that the first one has just this yield arrow, a single direction from the reactants to products, whereas in my equilibrium condition down here, I have both a forward and reverse. So what makes a strong acid strong is that it will completely dissociate into ions, whereas in a weak acid, I have an equilibrium condition between my reactant, which is my non-dissociated acid, and my H+. A strong acid dissociates completely, it makes more H+, and we know that H+ is something that makes an acid an acid. So for strong acids, a great definition, or bases, this applies to bases as well, is that they completely dissociate into ions. Whereas a weak acid or base has an equilibrium dissociation. Now, if we wrote our weak acid equilibrium more generally, we could say that's HA, goes back and forth between H plus and A minus. Now, if we wrote an equilibrium expression for our equilibrium for a weak acid, you'll notice this is going to be aqueous, this is going to be aqueous because they're both ions, and my HA, crucially, is still soluble, so it's still aqueous. If you looked in this bottle of vinegar here, you notice it's all aqueous, it's all in solution, but there's an equilibrium between the dissociated ions and the undissociated acid in there as well. And so if I wrote my equilibrium expression, we could say that K would be equal to the concentration of H plus times the concentration of A minus divided by the concentration of my HA, my undissociated acid. We define this as Ka, and Ka is my equilibrium constant for an acid dissociation. So just like the other equilibrium constants we've seen, except the acid, the A, specifically lets me know it's an acid dissociation. Now, you want to be familiar with some common strong acids and strong bases, and we've seen the 6 strong acids before, but just to list them again, our strong acids are HCl, hydrochloric acid, HBr, hydrobromic acid, HI, hydroiodic acid, and then we've got nitric acid, sulfuric acid, and then finally HClO4, perchloric acid. Every other acid that we're going to see is a weak acid. Now, a common type of weak acid that I want to make sure we know is organic acids. And when we have an organic acid group, that's always going to end with COOH. Or if they write it out with bonds, C double bond O and OH, attached to some other part of an organic molecule. Let's take a look at bases. For bases, a common base that we know might be something like sodium hydroxide. And again, that will dissociate, if it's a strong base, completely into sodium ions and OH minus. So more generally, what you can see is that we're going to have some type of a metal, something like M, with OH, go to M plus OH minus. That's my general reaction for a base. The common strong bases that we're going to see are group 1 hydroxides. So sodium hydroxide, lithium hydroxide, potassium hydroxide, and so on and so forth. Now, as far as weak bases go, these get a little bit more interesting. Weak bases are commonly not metal hydroxides, but are instead some base that's just its own molecular compound. And what that molecular compound can do is it can actually react with water. So my base is going to react with water, and it's going to be in equilibrium. If a base is acting like a base, it's going to accept a proton. That's one of our acid-base theories. And so I'm going to have that base accept a proton, become Hb plus, and make an OH minus. Now I can set up an equilibrium expression for this reaction. I take K, it's going to be equal to Hb plus times OH minus divided by the concentration of my base. Crucially, the water does not play a role in my equilibrium. My base is aqueous, but my water is a liquid, and liquids and solids don't show up in our equilibrium expressions. So that's our common reaction for a base. Now, a common example of this base is going to be some type of an organic base. And an organic base is often NH3, because NH3 is very able to accept a proton. And in fact, we're going to take a look at that equilibrium in just a second here. Now, very quickly, I'd like to go over the Arrhenius and Bronsted-Lowry theories of acids and bases, because we're going to see these a lot. In the Arrhenius one we've been talking about already. The Arrhenius theory of an acid is that acids produce H plus ions in solution. Now, not every acid is an Arrhenius acid, but most of them are acids that produce H plus ions in solution. Contrast that with the Arrhenius definition of a base. Arrhenius said that bases produce OH minus ions in solution. Now let's take a look at the Bronsted-Lowry definition. So the Bronsted-Lowry definition for us, fortunately for acids, is nearly the same thing. Bronsted-Lowry said that acids are proton donors. We can see how this is extremely similar to what we've seen before. If acids produce H plus ions in solution, they must be donating a proton, because a proton is the same thing as an H plus, a hydrogen ion, because a hydrogen atom has a positively charged nucleus with one proton in it and an electron. Well, if I strip that electron away and make it a hydrogen ion, all I'm left with is just that positive proton in the center. And so by creating H plus ions in solution, I am also donating protons. But the reason we've developed new acid-base theories is because they help us describe more things as acids and bases than we originally could. Take that weak base of ammonia before. NH3 doesn't seem to fit the Arrhenius definition of a base originally. It doesn't look like there's any OH minus in that. But we can also see that that NH3 is an proton acceptor. So bases, in my Bronsted-Lowry definition, are proton acceptors. And ammonia fits very well within that definition there. In fact, let's go ahead and take a look at ammonia and see what happens when we combine ammonia with water. If I react ammonia, NH3, with water, it's going to set up an acid-base equilibrium because ammonia is a weak base. And so I'm going to get an equilibrium reaction. Now, because it's a base, we know if we imagine taking this forward reaction, so going forward here in my equilibrium, NH3 is a weak base. And by the Bronsted-Lowry definition, NH3 from Bronsted-Lowry should go ahead and accept a proton. And so what it's going to form when it accepts a proton from that water is NH4+. Now, the other thing I'm going to form, because my water lost a proton, is OH minus. So the NH3 from a Bronsted-Lowry perspective accepts a proton, and so therefore it's a base. But we can also look at the ammonia from an Arrhenius perspective as well. From an Arrhenius perspective, we know that this NH3, when it got put in water, formed OH minus ions. The OH minus ions didn't come from the NH3, but because of its reaction with water, it produced OH minus ions, and so because of that, produces OH minus. We also therefore know that it's a base. But there's one more thing going on. This had to have been done in water. If I just have NH3 by itself, it's not an acid or base. I had to put it in water in order for it to be a base and produce a basic solution. The other thing that's in there then is the water. Now, if you look at the water here, that water accepted or donated a proton to my NH3. And so because of that, based on the Bronsted-Lowry definition, my water appears to be an acid. So therefore my water acts as an acid. And so what I have here is a reaction between a base and an acid. And indeed, on the other side, you know, acid plus base makes a salt. There's also water sticking around here as well. But I've made an ionic salt, ammonium hydroxide, NH4+, sticking with our OH minus here. So by looking at the forward reaction of my equilibrium, I can see how both of these things act as bases. Now, there's something interesting to be learned by looking at the reverse reaction as well. If we look at the reverse reaction, I have ammonium, NH4+, reacting with OH minus. That NH4+ seems to donate a proton to the OH minus to form water. That looks a lot like the Bronsted-Lowry definition if I donate a proton of an acid. So it sort of looks like this NH4 is an acid. And similarly, OH minus is an OH minus ion. And we know that bases produce OH minus ions in solution. And so if you think about it, either from Bronsted-Lowry or Arrhenius, where it produces OH minus, or from Bronsted-Lowry, where it accepts a proton, it looks like OH minus is a base. So we can see that this equilibrium is between a base and an acid, and a base and an acid on each side. And so what we've set up are what we call conjugate acid-base pairs. So a conjugate acid-base pair conjugate acid-base pair is a set of substances related in an acid-base equilibrium. So we can see up in our reaction here that this NH3 and our NH4+ are related. They form a conjugate acid-base pair. And so I can pair these up and say that NH4+ is the conjugate acid of NH3. We can predict that because by having NH3 accept a proton as a base, it forms a conjugate acid. Similarly, my water is in a conjugate acid-base pair with our OH minus. By accepting or donating a proton, my water acts as an acid and forms this conjugate base. Now we typically say the conjugates are on the product side of an equilibrium and the normal acid and base are on the reactant side of an equilibrium. And so if we were to name our conjugate acid-base pairs here, we would have NH3, NH4+ as one pair, and H2O, OH minus, as our other conjugate acid-base pair. The way we can identify these conjugate acid-base pairs is by looking at what is going to accept or donate a proton. By donating a proton, the H2O becomes an OH minus. By accepting a proton, NH3 becomes an NH4+, and I get my conjugate acid-base pairs, which we'll only ever see in acid-base equilibria. Well, that's an introduction to acids and bases. We took a look and saw how the definitions of acids and bases help us predict the different properties of acids and bases in an equilibria, and saw how a weak base, such as something like NH3, exists in an equilibrium between dissociated and undissociated forms. Thank you very much for watching. Have a great day.